In today's video, we're going to go over the synthesis of alkynes and some of the electrophilic addition reactions to alkynes. Last time in class, we saw that molten KOH with a dihalide would react in an elimination reaction to form an alkyne on the carbons between the two bromines. Just like with the synthesis of alkenes, where your BRs start is going to control the alkyne that you form. And so if we start with two BRs in the terminal position, we can change the alkyne I form to a terminal alkyne. In the first step of this reaction, the electrons on this amide would be donated to that proton to deprotonate it, which would kick these electrons up and kick Br off to give you this product with a Br and an H on the alkene. And then a second amide, see I started with excess, so there's more amides around, would come in and attack this proton, which would kick up and kick that Br off to give you this intermediate. The terminal proton of a terminal alkyne is more acidic than this proton here. And so as soon as this guy is formed, an amide, another one, can come in and deprotonate that to form this acetylide. And that's where this reaction is going to stop in step one. After step one is complete and you have completely this acetylide, the purpose of this water is just to reprotonate that terminal alkyne to give you one butene, and this is going to give you an OH minus. So if you're trying to synthesize a terminal alkyne, you have to go all the way to the acetylide first and then reprotonate it to get the terminal alkyne. Now that we've been over the synthesis of an alkyne in a couple of ways, I thought we would talk about how you might synthesize an alkyne from an alkane. And so what I've shown here is cyclooctane, and we really only know one reaction that cyclooctane can undergo, and that is a reaction with Br2 and light, which is going to form an alkyl bromide here. Now to form an alkyne, we need two leaving groups, and so you might want to treat this with another equivalent of Br2 and light. But that reaction isn't super selective. And so if we want to form explicitly one alkyne, there is a better method to do that. And so the first thing I want to do is to convert this to an alkene. So I'm going to use potassium tert-butoxide to ensure that I do just elimination and form cyclooctene here. And we know how to convert an alkene into a dibromide by reacting that with Br2. That's going to selectively form the trans dibromide. which we saw in the previous slide could be reacted with hot KOH to form an alkyne. Now I chose cyclooctane here as the cyclic molecule because an 8-membered ring is really the smallest ring that can incorporate an alkyne, because these bond angles here really want to be 180 degrees, but that's hard to do in a cyclic molecule, and so a cyclooctane is the smallest cyclic alkyne that's stable. Like alkenes, alkynes are areas of high electron density, and so they often react as nucleophiles. However, they are less reactive than most alkenes. When you think about the addition of HCl to an alkene, the rate determining step is the initial step, or the carbocation formation. And so that step involves donating electrons to the hydrogen and then kicking off that Cl to form this carbocation. If we look at the same rate determining step of the alkyne, I'm going to take these electrons and donate them to H and kick off that Cl. And that's going to form this intermediate here. This intermediate is a vinyl carbocation, and these are super unstable. And so this rate determining step is much slower than this rate determining step, which makes the addition of HCl to an alkyne much slower than the addition of HCl to an alkene. Because the vinyl carbocation intermediate we saw before, which looks like this, we gave electrons there and formed this vinyl carbocation. Because that's so unstable, many chemists believe that this goes through something called a pi complex. So instead of forming that, we're going to form this. And these dotted lines are meant to indicate a partial bond. And that proton has a partial positive charge, and this Cl has a partial negative charge. And this thing is called the pi complex. And since that vinyl carbocation is so unstable, many chemists believe that this is the actual intermediate that gets formed. And once that gets formed, Cl minus is going to come in and attack the most substituted side here, which is going to form this alkene with the Cl at the internal position, or the most substituted position. If we look at another example of an alkyne with HCl, again, the first thing that happens is we form a pi complex. Here, this time both sides are the same, and so Cl minus is going to come in, and it doesn't matter which side it attacks, and form this guy. Now, one of the best pieces of evidence for this pi complex intermediate is that most electrophilic additions to alkynes give you the trans product, like shown here. If it were going through a carbocation, remember that it would probably give you a mixture of cis and trans. However, alkenes, we said earlier, are more reactive than alkynes. So it's actually quite difficult to stop at this position. Most of the time, this is going to go a second time. And so often this reaction is run in the presence of excess HCl. And so I'm going to add another equivalent of HCl, and I'm going to give those electrons there and form here. And this could form one of two carbocations. The first one looks like this. Here, where I added a second hydrogen to the same carbon. The other one looks like this, where I put the hydrogen on the same carbon as the Cl and form this carbocation. This carbocation is preferentially formed because of resonance. This Cl has a lone pair that it can give down to that carbocation, just like we've seen with oxygen. And it forms this resonant structure. Here. And then a second Cl minus can come in and attack this carbocation to give you this as your final product. And so when you add HCl to an alkyne, if it's an internal alkyne, the first addition is not selective. Here, this Cl minus could have attacked either carbon. That first addition is not selective. However, once you put one Cl on that alkyne to form this alkene, the next addition is selective. You're going to form a gem disubstituted or gem dichloro compound, as shown here. Another example of reactions of alkynes is the halogenation of alkynes. And that reaction is very similar to the halogenation of alkenes. In the first step, electrons from the alkyne are donated to Br, which can send some electrons back and kick off this Br. That's going to form a three-membered ring with a Br and plus charge, and that alkene, or one of those pi bonds, is still present, and a Br minus. That Br minus is going to come from the opposite side as the bromonium ion and then break that carbon Br bond to give you the trans bromine addition across that alkyne. Just like in the hydrogen halide addition, this alkene is more reactive than the starting alkyne. And so often, to make sure we get a single product, this reaction is run in the presence of two equivalents of your halogen so that we're going to get a single product. So I'm going to put another Br2 in here. And this reaction is going to work just like an alkene. Attack, give some electrons back, and break the Br-Br bond to form another bromonium ion, like so, and a Br minus, which is again going to come in and attack the most substituted side and break that off to give you a tetrabromide where I have added two Brs to both carbons involved in the alkyne as the major product. That's going to wrap up today's video. We'll pick up with hydration of alkenes next time.